So this is the second session on moving bits for AI. I guess we all know that AI, generative AI, and machine learning is a big workload that is straining infrastructure, and new designs are coming up. And we have three very interesting papers in this session, 2 research track papers and 1 experience track paper. The first paper is on collective communication service. And Jingrong Chen is a 4th-year PhD candidate at Duke University, advised by Professor Danyang Zhu. His research spans from layer 4 to layer 7 networking with a focus on performance and manageability in end-host networking in cloud data centers. Please join me in welcoming Jingrong Chen.
Okay, now let's get started. Good morning, everyone. This is Jingrong. Today, from Duke. Today, I'm going to talk about MCCS, a service-based approach to collective communication for multi-tenant cloud. This is joint work between Duke and Meta. Collective communication over the years has become the de facto approach to synchronize data in distributed machine learning training and serving using various parallelization strategies. For instance, in data parallel training, gradients from workers are accumulated using all-reduced collective. In all-reduced, data buffers from all GPUs are reduced, and the results are written to a user-specified receive buffer on every GPU. According to a report, collective communication takes up to 42% of the overall training time of common LLMs in a TPU cluster. As a result, improving the performance of collective communication has always been a key research topic. Let's first take a look at how applications use collective communication today. At compile time, the application just links with a collective communication library. At runtime, the collective communication library determines collective strategies, for instance, whether to use a ring or tree-based algorithm. And this decision is based on some static rules like data sizes, number of GPUs, and type of links between GPUs, like NVLink or PCIe. And to our knowledge, all existing use cases for collective communication fall into this library-based, heuristic, or static rule-based approach, including NICO for NVIDIA GPUs and RICO for AMD GPUs. However, the library-based approach has a bunch of problems in a multi-tenant environment, for example, a public cloud or cluster shared by multiple teams in a company. In such a multi-tenant environment, we may or may not know the underlying physical network topology. As a result, the collective algorithm selection might not be optimal. Furthermore, with multiple jobs from different tenants in a shared cluster, we may want to enforce some policies, for example, to prioritize some time-sensitive critical workloads over non-critical ones. Besides, in a multi-tenant environment, jobs come and go. The available resources are dynamic, so as the optimal transfer schedule. So is it possible to adapt schedules to changing workloads? In addition to this, we may also want some sort of observability into the user's collective operations. A library-based approach falls short of these aspects, which also makes our design goal to address these issues. Let's take a closer look at current solutions. To improve or optimize collective algorithm performance, current solutions synthesize and optimize collective algorithm given the cluster topology. So there's an optimizer takes in the topology and generates a series of algorithms for different collective operation types and message sizes. So this stage is offline. Later, the generated algorithms are fed to the collective communication library at runtime, where it chooses one of the algorithms depending on the operation type and data size specified by the user. However, these solutions still optimize in a limited scope. Because synthesis happens in an offline stage, they cannot adapt to changing network utilization caused either by the background traffic or workloads from other tenants. Current solutions to performance optimization are mostly based on static information and only target for single job or tenant. And as for multi-tenant policy enforcement and dynamic reconfiguration, there is no current solution. So think about the fundamental reason about these limitations. If you look at the position of the collective communication library, it is linked and coupled with each single application. As a result, the collective communication library is loosely connected to the underlying cluster topology, because in a multi-tenant cluster, there's typically another layer of network abstraction which hides the underlying topology from the application. So it is loosely connected. And the collective communication library is also completely disconnected from other tenant applications who are also using the same collective library. So there's a great deal of optimizations we could have done here. On the other hand, there's a strong coupling between an application and its collective communication library, making it difficult to change the collective strategy and or implementation at runtime. We do not see much hope in continuing to optimize based on the existing library-based approach. This is because to solve these limitations, we want strong integration in a sense that the collective optimization directly consider low-level network topology and workloads from other tenants. We also want weak coupling in a sense that most of the collective functionalities are extracted out of the collective communication library into a centralized separate service. Therefore, inspired by MRPC, Managed RPC as a Service, we propose an alternative architecture where collective communication is provided as a service by the infrastructure owner. Our architecture, Managed Collective Communication Service, is shown on the right side. In MCCS architecture, collective communication is directly integrated into the cloud network and provided as a service. We first have a shim library to replace the original collective communication library, but unlike traditional CC libraries, it does not contain any implementation of the collective algorithms. What it only does is to connect to an MCCS service through shared memory queues and shared memory GPU buffers. On each host, there's a single MCCS system service, which is persistent and shared across all applications. So with such a service-based approach, we can do a bunch of things that we cannot do before. However, implementing such an architecture is non-trivial, so there are several challenges. First, how can we decouple implementation from the application while maintaining a similar collective API? Second, how can we flexibly support scheduling policies at different levels? Finally, how can we dynamically reconfigure collective strategies at applications runtime with minimal overhead? In this talk, we'll omit the second challenge, which you can read the paper for more details. So before starting with the first challenge, let's look at an example of collective interface. In Nico Altogether as an example, there were 4 parameters: send buffer, receive buffer, message size, and CUDA stream to enqueue the operation on. Because the application and the MCCS service are 2 separate processes, we want both processes to safely access the same GPU buffers. So extra care of memory management must be taken. So this includes memory sharing and address translation. Another problem is about the last parameter here, which is a CUDA stream. A CUDA stream is simply a queue of GPU operations, where the GPU operations in the CUDA stream must be executed in order on a device. So it is about synchronization or ordering. MCCS must maintain the same CUDA string semantics, even if it's in another process. So let's tackle them one by one. First is memory management. To allow both processes to use the same shared GPU buffer, we must do some extra work around CUDA malloc. That's why we provide MCCS malloc. Internally, MCCS malloc sends the allocation request to the MCCS service. The service leverages CUDA memory APIs and CUDA IPC mechanism to allocate a device-registered memory buffer and pass a handle to the memory buffer back to the user shim. When issuing a collective operation like MCCS altogether, the shim sends the altogether request to the MCCS service, as well as its parameters. But instead of passing raw pointers or virtual addresses for the send buffer and receive buffer, we pass an ID. So the ID of the memory region plus an offset. So this allows MCCS to safely locate the underlying GPU buffers, so the memory sharing and address translation is done this way. Next is the synchronization issue. The issue is that we want the collective operation in the MCCS service, which is the all gathered here in the blue box, to start only after compute kernel 1 in the application is complete, and likewise for compute kernel 2. However, a CUDA stream is local to a process, so there's no direct way for one process to wait for a stream inside another process. So this problem is really about interlocking CUDA activities between two individual processes. Fortunately, CUDA provides a standard IPC mechanism which allows creating a CUDA event with inter-process capability. So we just allocate an inter-process CUDA event and pass it to another process. Then in the other process, we can call CUDA stream waiting event to wait on that event. With such a mechanism, we can implement synchronization and enforce ordering between two individual CUDA streams. In practice, whenever the user calls into a collective operation like allgather, the shim library creates a CUDA event as a synchronization point and passes it to the MCCS service. So this is showing step 1. In step 2, the MCCS service first waits for that event in its local CUDA stream. Then it launches allgather kernels and creates another CUDA event which represents the completion of that allgather and pass it back to the user shim. So this is showing step 2. On receiving the MCCS event, the user shim just waits for the completion of that event in its own stream. In this way, all compute kernels later in queued will only be started after the allgather's completion. That's how we maintain the ordering. At this point, we are able to maintain the API semantics as a regular collective communication library. Now we briefly go through some policies we support. Imagine what you can do by putting the collective communication library into a centralized service. On the lower level, the network has multiple passes. So instead of relying on ECMP for load balancing, we can just assign a path for each flow in the network to explicitly avoid flow collision whenever it is possible. We can also enable fine-grained traffic control. This is because MCCS controls when to send traffic. So with this ability, MCCS can even interleave two applications' traffic to increase network utilization. On a higher level, a common problem of running collective jobs on a public cloud is that the rank assignment may not fit well into the underlying physical network topology, which can cause too much cross-rack traffic. So this figure here shows a production trace from Meta. So when the job size increases, it is almost inevitable to avoid unnecessary cross-rack traffic. But with MCCS, we know the network topology, and we implement the algorithm ourselves. So it is easy for us to do optimal rank assignment. In MCCS, we not only support various policies, we also want to allow policy change at runtime. This we call it dynamic reconfiguration. It is challenging because for some configuration changes, if not all workers apply the change at the same time, the job may hang. But if we simply block the data path for applying the change, it works, but the performance is not ideal. Here, we use ring configuration as an example to demonstrate. We want to change the order of the ring or reduce. So there's a reconfiguration request. Say every worker has received that request except GPU 0. And all workers except GPU 0 update to the new ring. Then there's an all reduce. So GPU 0 will just use a different ring from all other workers. So the all reduce may just hang forever. To address this problem, MCCS performs an all-gather to collect the sequence number of every worker's latest collective operation. This all-gather is launched on the control path, so it does not block the data path. After the all-gather completes, we check the sequence number to see if everybody is in sync and to see if there's any outstanding collective operations. If they're not in synchronization, we just still use the old ring for future all reduces. Only after all the outstanding collective communication are complete, everybody updates to the new ring, so the reconfiguration is done. The key takeaway here is that the all-gather-based synchronization only happens during reconfiguration and does not introduce any overhead to the fast data path. To evaluate how MCCS actually performs, in this talk, we focus on answering 3 questions. Can MCCS improve performance of a single application and multiple applications? And can MCCS QoS capability benefit training workloads? In our evaluation, we explore 2 policies. The first, we call it optimal ring, where we use the best rank assignment to minimize cross-rack traffic. The second, we call it best fit fair flow assignment, which avoids flow collision on network multipasses. We first evaluate a single application all-gather performance on 8 GPUs, where each host has 2 GPUs. Each host also has a 100 gigabits per second NIC for inter-host communication. The bandwidth on the links between switches is 50 gigabits per second. Compared with NICO, MCCS achieves a speedup of 2.8 times on average. We also compare MCCS without flow assignment, which is the brown line here, to NICO with optimal ring, which is the orange line here. We can see that MCCS has negligible overhead on larger messages. But we also note that MCCS does have some overhead for smaller messages. This is caused by multiple rounds of data passing in our current prototype. To evaluate multiple applications' performance, we place 2 applications, each using 4 GPUs across 4 hosts. So each GPU on the host can use half of the NIC's bandwidth. In this case, MCCS also outperforms NICO for both applications, achieving a speedup of 2.5 times on average. To show MCCS QoS capability, we explore 2 extra policies. One just dedicates network passes for high-priority applications, and the other just masks application traffic with time windows based on Cassini. We show the throughput of 3 training workloads normalized to the values between T2 and T3. At first, there is only job A, and as B and C arrive, the throughput of A is degraded. At T3, we prioritize A using priority flow assignment, improving A's throughput by sacrificing B and C. At T4, we further prioritize B over C using the traffic scheduling policy. So MCCS again effectively enforces such QoS policy. To summarize, the collective communication as a library misses some important opportunities in performance optimization and has no manageability in a multi-tenant environment. Therefore, we propose MCCS to re-architecture collective communication into a managed service-based approach. MCCS maintains similar APIs and enables multi-tenant and topology-aware scheduling. It also supports low-overhead dynamic reconfiguration of collective strategies. You can scan the QR code here to find our code base. Thank you for listening.
Any questions?
Did you do any micro measurements for that synchronization overhead? How much time does it consume?
You mean measure or do the
measure or micro benchmark?
I'm not sure if we have done that before. You mean just blocking the data path or using our approach do not block data path? Which one?
So how much does that impact the data path for that synchronization to complete?
I'm not sure if I can just answer or remember that numbers. But I can definitely check the number and talk with you offline.
Dong-Soo Han from KAIST. How do you compare your work against the one that Alibaba did with the GPU intensity? And can you support a policy like that prioritize jobs with higher GPU intensity, like the Alibaba people did?
I'm not sure I'm aware of that, what they have done particularly.
One of the first papers in the first session of SIGCOMM',
sorry.
You can find them in the audience later.
Yeah, sure. I guess I can discuss them later.
Good, thanks.
After I check that paper. Yeah.
Anything else? Anybody?
Question. Hi, great talk. This is Jingjun from Huawei. So in your problem statement, you said the current collective library has issues loosely coupled with the network. But in your talk, you just mentioned topology. What else you did for your coupling part?
So, you know, the underlying infrastructure, the network is usually shared in a class or in a cloud. So it's a shared infrastructure. So apart from the topology, like the flow are also shared. So that also includes flow scheduling, I guess. So in our work, we mainly use the topology information to do topology-aware rank assignment. That's first thing. And we also do flow assignment to ping the flow or assign the flow to a explicitly to one of the network paths in the network. So that's another thing we do.
But I think that's NCCS also does that, right? I don't see any difference there.
What also does that?
Assign the flow to the path. I mean, scheduling the flow to the path. That's exactly what the
Yes. So the difference is that we are enforcing this at the application layer, or we do not need to enforce, like we do not need to change the network setting or switch setting. Sometimes that's not even possible, right? So that's, I guess, the main difference here.
Okay, thank you.
Let's thank the speaker again. Yeah.
Okay, thank you.